Hello, future engineers, subscribers, viewers, and students. Here is the continuation of plane and spherical trigonometry 3. So, properties, characteristics of spherical triangles. So, some examples of great circles are the meridians of the Earth and the equator, having the same diameter as the sphere. So, if we have the sphere here, then we have the poles, axis through the poles, that's the axis of the sphere, and it passes through the center of the sphere, which is marked O. Great circles are through point O, but those circles not passing through O perpendicular to the axis are called small circles, as shown in the figure. So we define a small circle as a small circle of the sphere is the circle constructed by a plane crossing the sphere through any other point, not the center of the sphere. So that's the definition of a small circle. Then the polar distance, which is denoted by capital P sub 1. So the polar distance P sub 1 of a circle is the least distance on a sphere from a point on the circle to its pole. So that's the polar distance, the least distance on a sphere from a point on the circle to its pole. So the nearest pole, of course, because that's the least distance. So if we have the circle here and we draw the poles and we have a small circle, the great circle passes through the center. So the polar distance is the distance from the pole to the point on the small circle. So this distance here is the polar distance of that circle, T sub 1. While the polar distance of the great circle is, of course, 90 degrees. So this is P sub 1, and the polar distance of the great circle is 90 degrees, as shown in the figure. Then another definition that can be cut from a sphere, solid sphere, is a spherical wedge. So we define a spherical wedge as a solid cut from a sphere by diametral or dihedral planes. So that's a spherical wedge. So I use watermelon slice here, perfect slice, which passes through the axis, and we form two dihedral planes, and the skin area is called the spherical loon. So it is surface area loon. So if this is the watermelon that is cut perfectly by two dihedral planes through the axis, so that's the wedge, the solid, the volume, and the skin area is the spherical loon. So that's the wedge, spherical wedge, and this is the spherical loon. Then there are important propositions for spherical triangles. So the first one, if equal angles of a spherical triangle are equal, the sides opposite are equal, and conversely. So it is similar to that of a plane triangle, where for isosceles triangles, two angles are equal and the sides opposite the equal angles are also equal, and conversely. So it's easy to recall this because the characteristics of spherical triangles are similar to that of plane triangles. If two angles of a spherical triangle are unequal, the sides opposite are unequal, and the greater side lies opposite the greater angle, and conversely. So it's also not a characteristic that is to be worried about, because this characteristic is also true for plane triangles. Of course, if we have a triangle and we have the smallest angle, the biggest angle, the side opposite the smallest angle is the shortest side, and the side opposite the biggest angle is the longest side, which is true also here. Then third, the sum of two sides of a spherical triangle is greater than the third side, which is the same as in plane triangles. In fact, I make it specific that the sum of the shorter sides of a triangle must be greater than the longest side. So here, this is the original statement about triangles. The sum of two sides of a spherical triangle is greater than the third side. So which is also true for plane triangles. So there's nothing to worry about this characteristic. So that is A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A. Then fourth, the sum of the sides of a spherical triangle is less than 360 degrees. So the sum of the sides of a spherical triangle is less than 360 degrees because the maximum side is 180 degrees and no two sides can be 180 degrees or else no triangle can be formed. So the other two sides should be less than 180 degrees if the longest side is 180, that's the maximum. So therefore, from the property earlier that the sum of any two sides should be greater than the third side, and it's true if the other two sides are less than 180 but more than half of 180. So therefore, it means that 0 degree is less than A plus B plus C less than 360 degrees. So the statement, the sum of the sides of a spherical triangle is less than 360 degrees. So take note that the sides of a spherical triangle are expressed as angles, not by distance, units of length, but we can also express that as units of length, but they are expressed as angles. Of course, if the radius of the sphere is known, then we can compute the corresponding sides in meters or in units of length. The sum of the interior angles of a spherical triangle is greater than 180 degrees. Of course, because if you notice the spherical triangle, the interior angle is greater than the corresponding plane, that corresponding interior angle of a plane triangle because of the curved part of the spherical triangle. So definitely the interior angle of a spherical triangle is greater than the corresponding interior angle of a triangle. Therefore, if each interior angle of a spherical triangle is greater than the corresponding interior angle of a plane triangle, then the sum of the interior angles of a spherical triangle would be greater than 180 degrees. And it should be less than 540 degrees, which is 3 times 180 degrees. So, right, because the interior angle for a triangle to be formed must be less than 180 degrees. Each interior angle of a spherical triangle must be less than 180. So if each is less than 180 times 3, so that's 540. In other words, so this is 0 degree is less than A plus B plus C less than 360 degrees for that statement. So 5, the sum of the interior angles of a spherical triangle is greater than 180 degrees but less than 540 degrees. So if you draw the spherical triangle, you will notice that the interior angle of a spherical triangle is indeed greater than the corresponding interior angle of a plane triangle. So therefore, the sum of the interior angles should be greater than 180 degrees, because the sum of the interior angles of a plane triangle is 180, exactly 180. And since the interior angle of a spherical triangle is greater than the corresponding interior angle of a plane triangle, so it follows that the sum of the interior angles of a spherical triangle is greater than 180 degrees. But it is less than 540 degrees because the interior angle of a triangle should be less than 180 degrees each. So times 3, that's 540 degrees. So it follows that the sum of the interior angles of a spherical triangle should be less than 540 degrees. So 180 degrees is less than angles AB plus C and less than 540 degrees. The sum of any two angles of a spherical triangle is less than 180 degrees plus the third angle. So this is true because each interior angle, as I said, is less than 180 degrees. So it follows that the sum of any two angles of a spherical triangle is less than 180 degrees plus the third angle. So that is angle A plus B is less than angle C plus 180 degrees. A plus C is less than angle B plus 180 degrees, and so on and so forth. So B plus C is less than 180 degrees plus A. So like that. Then we proceed to right spherical triangles. This is just the introduction. So a right spherical triangle is one with a right angle, just like a right triangle. A spherical triangle with two right angles is called birectangular spherical triangle. Then when all of the interior angles are each 90 degrees, which is possible for a spherical triangle, then it is called trirectangular spherical triangle, when all interior angles are each 90 degrees. Then let's proceed to what we call this important concept, Napier circle or Napier's circle or Napier's pentagon. This is a mnemonic aid to easily find relations between the angles and the sides of a spherical triangle. So it is like the 6 equal ratios, but this is different because we have two further rules here, which we call Napier's rules for right spherical triangle. And the two rules are the sin cos op and the sin tan ad. Sin cos op, I will explain that as we move on. So let us say we have a right spherical triangle wherein the right angle is angle C. These are the parts of the right spherical triangle. And we draw the Napier circle or Napier circle. And there are 5 parts, excluding this 90-degree angle, angle C. And the ruling is, beginning with B in the same direction here, elements of the right spherical triangle, we begin with B, the next would be A. We bypass C because it is not part of this Napier circle. So after B is A in counterclockwise direction. Then all elements B, C, and A opposite to the right angle element would be replaced by their complements. So B, A, then complement of B, complement of side C, and complement of angle A. So complement of angle B, complement of side C, and complement of angle A. Then we apply these Napier's rules for right spherical triangle. The first rule, rule 1, is the sin cos op rule. The meaning of this acronym or abbreviation should be the sine of any middle part of this Napier circle is equal to the product of cosines. Cos means cosines of opposite parts. Since there are 5 parts, we can derive 5 formulas. I will present the 2 formulas here, and the 3, I want you to derive the 3. I'll just write it here so that you will know how to apply this first rule here. So that you don't need to memorize, just memorize sin cos op rule and the sin tan ad rule. The rest, you will know how to derive the 10 formulas after applying the 2 rules. So that is, if I make cosine of complement sine of this middle part here, opposite to this element would be A and B. So that is sine of coc is equal to cosine of A times cosine of B, applying the first rule. Because the sine of any middle part is equal to the product of the cosines of opposite parts. So that is sine of complement of C equals cosine of A times cosine of B. I hope that you know it after applying this rule 1 here. You just select any of these 5 parts as the middle part, and it should be the product. The sine of that part is equal to the product of the cosines of opposite parts. So the opposite to complement of C would be A and B. So that's why sine of coc is equal to cosine of A cosine of B. But sine of complement of C is cosine of C. So therefore, the first formula that we can formulate is cosine of side C equals cosine of side A times cosine of side B. Then the second one would be cosine of complement of A. Opposite to this would be side A and complement of B. So sine of complement of A equals cosine of A times cosine of complement of B. And since sine of complement of A is simply cosine of A, and cosine of complement of B, angle B is sine of angle B. So cosine of A is equal to cosine A, then sine of angle B. So you don't need to memorize, you just memorize this rule, sin cos op. Then after memorizing this rule and doing this Napier circle, you can establish these 5 formulas. The other formulas which I want you to derive would be sine of B, side B equals sine of angle B, sine of side C. Then fourth, sine of side A equals sine of C, sine of angle A. Then fifth, cosine of angle B equals sine of angle A, cosine of side B. So I want you to derive 3, 4, and 5 applying this rule. Then we proceed to the next rule, which is the sin tan ad rule. It means that the sine of any middle part is equal to the product of the tangents of adjacent parts. Ad means adjacent. So beginning with sine of complement of C, adjacent parts would be complement of A and complement of B. So sine of coc is equal to tangent of coA times tangent of coB. So that's the application of that rule. Sine of coc equals tangent of quantity coA, tangent of quantity coB. So sine of coc is cosine of C. Tangent of coA is cotangent of angle A. Tangent of coB is cotangent of B. So the first formula from here would be cosine of side C equals cotangent of A, cotangent of B. Then, for formula 2, for instance, sine of coA would be equal to tangent of B, tangent of coc. So sine of co A is cosine of A. Tangent of B is still tangent of B, while tangent of co C is cotangent of C. Therefore, the second formula that we can formulate would be cosine of angle A is equal to tangent of side B, then cotangent of side C. So therefore, cosine of A equals tangent B cotangent of side C. So likewise, I want you to derive 3, 4, and 5, formulas 3, 4, and 5, which are sine of side B equals tangent of side A cotangent of angle A. Fourth, sine of side A equals tangent of side B cotangent of angle B. And fifth, cosine of angle B equals tangent of side A cotangent of C. You need to derive this, although you're not allowed, or my suggestion is do not memorize these formulas. Just familiar with the two rules, sin cos op and sin tan an rules. You should know how to draw the Napier circle. Only elements A and B would be at ease, and opposite to the 90-degree angle, which is angle C, would be replaced by their complements. Then apply the two rules. You can derive all these 10 formulas. You don't need to memorize, because even myself cannot memorize these formulas. But I can derive all those 5 because I can only memorize the two rules, the sin cos op and the sin tan ad rules. Then we have important rules for right spherical triangles. So first rule is, important rule is, in a right spherical triangle, an oblique angle and the side opposite are of the same quadrant. So of course, it is an oblique angle, and therefore the side opposite are of the same quadrant. So meaning to say, if the angle is in the first quadrant, then the side opposite it would be in the first quadrant also. It is acute or less than 90-degree angle. If it is obtuse, then it is in the second quadrant. Obtuse, between 90 degrees and 180 degrees. When the hypotenuse of a right spherical triangle is less than 90 degrees, the two legs are of the same quadrant, and conversely. So meaning to say, because the hypotenuse is less than 90 degrees, then the two legs would be on the same quadrant, and conversely. So it would be the same. So it would be in the first quadrant because the hypotenuse is less than 90 degrees. That's the idea then. Then third, when the hypotenuse of a right spherical triangle is greater than 90 degrees, one leg is of the first quadrant and the other of the second quadrant, and conversely. So if the angle is less than 90 degrees, by the way, from property 2, the two legs are of the same quadrant, meaning say they are on the first quadrant only when the hypotenuse is less than 90 degrees. But in this case, when the hypotenuse of a right spherical triangle is greater than 90 degrees, then one leg is of the first quadrant and the other leg would be on the second quadrant. So one is less than 90, the other is greater than 90. That's the meaning of this property. Then we proceed to, because this is the second part, there is still third part. The third part would be on problem solving, and plane and spherical trigonometry 4 would be about the applications of the spherical trigonometry, and we will deal with the terrestrial sphere, which is the Earth, the theoretical treatment of the Earth. So first problem, evaluate quantity tangent of arcsine of 3/5 plus inverse tangent of 3. So for the calculator technique, you can easily compute this. You just press tangent, then quantity inverse sine of 3/5. plus inverse tangent of 3, and you will get the answer -3 right away. So that's for the calculator technique, and you should do that. Or this is the official solution, because these are angles. I'll call this alpha. So I'll call that alpha, and the second one is beta. Then we'll have to expand tangent of quantity alpha plus beta, which is equal to tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. So that's the crucial thing about this problem. If you cannot memorize tangent of alpha plus beta, I ask you to derive it again by you, so that in case you will forget, you can easily recall if you know the derivation, of course. So although I already mentioned the calculator technique, you can easily obtain the value of this problem, tangent of arcsine of 3/5 plus arctan of 3, using your calculator. You will get -3. But I'll just present this official solution for those who are taking up trigonometry, because this solution is not acceptable by your teacher definitely. This one is acceptable. This is the solution supposedly. Tangent of alpha is because we have arcsine of 3/5. So if you draw a right triangle, then this is the angle alpha. The opposite should be 3, hypotenuse should be 5, and the adjacent side should be 4. So assuming that this angle is in the first quadrant, because there's no other information, it is not mentioned here. So therefore x should be 4, and tangent of beta is just 3. There's no need to draw a triangle. So the tangent of alpha is 3 over 4. So 3/4 plus 3 over 1 minus 3/4 times 3. So 3/4 plus 3 over 1 minus quantity 3/4 times 3. And that is equal to 3. -3 rather. Then the next problem, find the equivalent expression for cosine of 2 arcsine of x. So arcsine of x is an angle. So if I denote that as theta, so it's like finding the equivalent expression for cosine of 2 theta. And cosine of 2 theta, if you can remember, is cosine squared theta minus sine squared theta. It is also equal to 1 minus 2 sine squared theta, and it is also equal to 2 cosine squared theta minus 1. There are 3 expressions for cosine of 2 theta. 1 minus 2 sine squared theta, cosine squared theta minus sine squared theta, and 2 cosine squared theta minus 1. So I select this because assuming this is one of the choices, so it looks like this. And if theta, arcsine of x is theta, so sine theta is equal to x. So that means opposite of theta is x, hypotenuse is 1. So that's why sine of theta is just x over 1, or simply x. So cosine of 2 arcsine of x therefore is equal to 1 minus 2 times x over 1 square. So simplifying, that's 1 minus 2x squared. For the calculator technique, all you have to do is substitute a value of x. So for instance, x is, I suggest 0.25. You can evaluate cosine of quantity 2 arcsine of 0.25. So cosine of 2 arcsine of 0.25, then you will have the value. And evaluate the choices. one of them is 1 minus 2 times this value here, 1 minus 2 times 0.25 squared, and this should be equal when x is 0.25. So that's the calculator technique. So if x is 0.5, then the value is also 0.5 because arcsine of 0.5 is 30 degrees, and 30 degrees is pi over 6 radians, or simply 30 degrees times 2, 60 degrees, and cosine of 60 is 1/2, and this will give us 1/2 when x is 0.5. 1 minus 2 times 0.5 squared, that's 1/2. So that's for the calculator technique. So let's proceed. So 1 minus 2x squared, that's the answer. Okay, problem 3. For any triangle, find x if arctan of quantity 1 plus x plus arctan of 1 minus x equals arctan of 1 over 18. Now for the calculator technique, all you have to do is set your calculator in the radian mode, then type this arc inverse tangent of quantity 1 plus alpha x plus inverse tangent of quantity 1 minus alpha x equals inverse tangent of 1 over 18. Then shift solve, try a value of x which is, let us say, 0.5, then your calculator will give you the answer. That's for the calculator technique. Then for the official solution, because these are angles, inverse tangent functions, so I'll call this alpha, the second term beta, and the right side term as theta. So alpha plus beta equals theta. Taking tangents on both sides, tangent of quantity alpha plus beta equals tangent of theta. Then expand tangent of alpha plus beta, which is tangent of alpha plus tangent of beta, all over 1 minus tangent of alpha, tangent of beta, and equals tangent of theta. So it is a must that you should be able to expand tangent of alpha plus beta, or else you cannot solve this. But if you know the calculator techniques, then that's your way of solving it. But this is for those who are taking up trigonometry at present, high school students maybe. This is the accepted solutions by your teacher. So tangent of alpha is 1 plus x, tangent beta 1 minus x, all over 1 minus quantity 1 plus x, then 1 minus x equals 1 over 18. So the numerator is 2 after we cancel x. So 2 times 18 is 36. Then the right side would be 1 times 1, which is 1. This is 1 minus x squared if we expand. So 36 equals 1 minus quantity 1 minus x squared. And if you simplify the right side, that's just x squared. So 36 equals x squared, or x is plus minus 6. But if in the choices it is positive 6 that is present, then the answer is 6. The solution to this problem is plus minus 6. Then I want you to try substituting negative 6 if the equation is satisfied for negative 6. If it is satisfied, then negative 6 is also a solution. For high school, but in the board exam, because there are choices, then the answer is just 6. Then problem 4, for any triangle ABC, tangent of angle A plus tangent of angle B plus tangent of angle C is 5. Then find the value of 10 divided by tangent of A times tangent of B times tangent of C. So A plus B plus C is 180 degrees. The sum of the interior angles of a triangle is 180. Taking tangents, and we group A and B as one angle, then C the other angle. So tangent of quantity A plus B plus C equals tangent of 180, and tangent of 180 degrees is, take note, it is 0. So expanding, we have tangent of A plus tangent of B all over plus tangent of C all over tangent of quantity A plus B plus tangent of C all over 1 minus tangent of A plus B, tangent of C equals 0. 0 times this denominator is 0. Then let's expand tangent of A plus B, which is tangent of A plus tangent of B, all over 1 minus tangent of A, tangent of C, then plus tangent of C equals 0. Multiply everything by 1 minus tangent A, tangent B. Then we'll have tangent of A plus tangent of B plus tangent of C times this, which is tangent of C minus tangent of A, tangent B, tangent C equals 0. So tangent of A plus tangent of B plus tangent of C minus tangent of A, tangent of B, tangent of C equals 0. So that means tangent of A plus tangent of B plus tangent of C equals tangent of A plus times tangent of B times tangent of C. Since tangent of A plus tangent of B plus tangent of C is equal to the product of the tangents, you can try 50, 60, and 70 degrees for A, B, and C respectively, and verify that the sum of the tangents of angles 50, 60, and 70, which is 180 degrees, if you add, is equal to the product of the same angles, tangents of the same angles. So in this problem, this 10 over tangent of A, tangent of B, tangent of C, which is equal to tangent of A plus tangent of B plus tangent of C, when the sum of the angles A, B, and C is 180 degrees. In this case, it is equal to 5, so we just replace this by 5. So 10 over 5 is 2. Therefore, it is 2. Of course, when the angles A, B, and C are 50, 60, and 70 degrees, of course, the sum would be equal to the product, but not necessarily 5, because the angles A, B, and C are not 50, 60, and 70 specifically. You look for combinations that such that the sum and product would be the same, equal to 5. But that's no longer a problem. We just verified that the sum of the tangents of angles that add up to 180 is equal to the product of the tangents of the same angles. So therefore, this is 2. The answer is 2. Problem 5. A car with a wheel diameter of 2 feet covered a distance of 26 miles in 39 minutes. Find the angular speed of the wheel in revolutions per minute in RPM. So we have the speed is 26 miles in 36 minutes. So that would be in miles per minute. So we convert that to revolutions per minute. First, 1 mile is 5,280 feet. So we multiply this by 5 to 80 feet per mile. And cancel mile, the units now is feet per minute. And we know that 1 revolution is 1 circumference. And circumference is pi times diameter, or 2 pi r. I'll just use pi times diameter because the diameter is 2 feet here. So we multiply further by 1 revolution per pi d, pi times 2 feet. Then that would now be in revolutions per minute. Using your calculator, it is equal to 560.2 feet. So next, problem 6. From 6:15 a.m. to 6:40 a.m. of the same day, what length of arc is described by the minute hand of a clock 12 centimeters long? So it is just the arc distance S, which is radius times central angle, and when the time is 6:15 between 6:15 to 6:40, the minute hand is pointing the 3 mark initially. Then at 6:40, the minute hand is now pointing the 8 mark. The angular spacing between the 3 to 8, so 3 to 4, 5, 6, 7, 8, so that's 5 angular spacing, and the angular spacing between marks is 30 degrees. I hope that you know that. So 30 degrees times 5 is 150 degrees. So theta is 150 degrees, and 150 degrees is times pi over 180 is 5 over 6 of pi radians. And S is radius times central angle. The central angle is 30 degrees times 5, so 150 degrees, and that is 5 over 6 pi. Substitute S equals 12 cm times 5 pi over 6, and that is equal to 10 pi centimeters. Then the last problem, 7, for this video. The area of a regular pentagon is 265.76 centimeters square. What is the length of the apothem? The apothem is the radius of the circle inscribed in a regular polygon. In this polygon, it is a pentagon, specifically 5 sides. And let's draw the figure. This is the circle that is inscribed in this regular pentagon. Its radius is the apothem. The central angle of each triangle is in general 360 degrees divided by n. So we will denote the radius of the circle circumscribing the regular polygon as big R. So the radius is capital R, but we are looking for the small r, the apothem. This angle, the measure of this angle in general is 360 degrees over n. In this case, in this particular problem, 360 degrees over 5, because there are 5 sides. The area of a triangle is, if you can recall, is 1/2 product of adjacent sides, which is big R and big R, times sine of the angle between those sides. So the area of a triangle, therefore, for this regular polygon is 1/2 r square sine of 360 degrees over n. Since there are n identical triangles, in this case n is 5, so the general formula for the area of a regular polygon with n sides would be n times 1/2 r square sine of 360 degrees over n. So the formula for apothem, therefore, from this right triangle, because this is the line perpendicular to the opposite side, and the measure of this angle is half this interior angle of this triangle, so it is half of 360 degrees over n, 180 degrees over n. So this small r here is big R, hypotenuse, cosine of 180 degrees over n. That's our working formula, but we need to solve for big R first. From this area of triangle, which is equal to n times 1/2 of r square sine of 360 degrees over n, where n is 5 in this case. So 265.76 equals 5 times 1/2 r square, big R square sine of 360 degrees over 5, and that is 72 degrees. Solving for r, big R is 10.572 cm. Finally, substitute here. Small r is 10.572 cosine of 180 degrees over 5. So using your calculator, small r, or the apothem, is 8.553 cm. So that's it for this video. I hope that you were able to follow the explanation, solutions, and you can recall properties, especially for spherical triangles.